In this video, we will introduce the third of the five major classes of organic reactions, elimination reactions. We'll explore the two main types, E1 and E2 reactions, covering their key components, understanding their differences, and identifying the reaction conditions that favor one mechanism over the other. We'll take a closer look at how carbocation rearrangements, a key type of organic reaction, influence the outcomes of E1 and SN1 pathways, and discuss factors that mediate competition between these two reaction mechanisms. In the previous video, we explored substitution reactions. Let's take a moment to review the key components and factors that drive these reactions. In substitution reactions, the two main reactive partners are the nucleophile and the substrate. The nucleophile replaces the leaving group, which is attached to the electrophilic alpha carbon of the substrate. In SN2 reactions, the process occurs in a single concerted step, where the nucleophile attacks the electrophilic alpha carbon of the substrate, while the leaving group departs simultaneously. This reaction requires a strong nucleophile and a weak base, proceeds faster with less substituted substrates, and is most efficient in a dipolar aprotic solvent. For SN1 reactions, the process occurs as a stepwise reaction with two distinct steps. First, the leaving group departs from the substrate, forming a carbocat ion intermediate. Then, the nucleophile attacks the positively charged carbocat ion in a separate step to complete the substitution. This reaction is favored by a weak nucleophile and weak base, proceeds faster with more substituted substrates due to carbocat ion stability, and is most efficient in a polar protic solvent, which helps stabilize the leaving group and the transition state via hydrogen bonding, lowering the energy barrier for carbocat ion formation. Elimination reactions involve the same reactive partners as substitution reactions, but occur under different conditions. Instead of the nucleophile replacing the leaving group, as in substitution reactions, elimination reactions lead to the formation of an alkene. This occurs when a hydrogen atom is removed from the beta carbon, resulting in the formation of a pi bond between the alpha and beta carbons, which causes the leaving group to depart from the alpha carbon. This process typically requires a reagent that acts as a poor nucleophile but a strong base. Recall that nucleophilicity decreases as steric hindrance increases. Therefore, bulky alkoxides like tert butoxide are commonly used in elimination reactions, as their strong basicity promotes elimination, while their steric bulk discourages substitution. Let's take a moment to discuss an important rule that helps predict the alkene products formed in elimination reactions. Zevs rule. This rule states that the alkene resulting from the removal of a hydrogen from the beta carbon with the fewest hydrogen atoms is typically favored and forms in greater amounts. In other words, elimination reactions generally favor the formation of the more substituted alkene, where the double bond forms between carbons that have the most carbon substituents. Alkenes become more stable as the number of directly attached carbon groups increases, making more substituted alkenes generally more thermodynamically stable. Now that we have a sense of alkene stability, let's take a closer look at the two main elimination reaction mechanisms, starting with the E1 mechanism. The E1 reaction begins with the departure of a leaving group, resulting in the formation of a carbocat ion intermediate, similar to the mechanism seen in SN1 reactions. In this example, a tertiary bromide undergoes an E1 reaction and the bromide ion leaves, forming a tertiary carbocat ion. The same stability trends that govern carbocat ion formation in SN1 reactions also apply to the rate of E1 reactions. More stable carbocat ions, such as those that are more substituted, form more readily. Once the carbocat ion is formed, a proton from an adjacent beta carbon is removed by a base, and the electrons from this proton are used to form a pi bond with the carbocat ion, resulting in the formation of an alkene. The name E1 stands for elimination unimolecular, referring to the rate-determining step of the reaction. Similar to SN1 reactions, the rate of an E1 reaction depends solely on the concentration of the substrate, with the rate-determining step being the departure of the leaving group to form a carbocat ion intermediate. Experimentally, the rate of E1 reactions is fastest for more substituted substrates, as the rate is directly proportional to the stability of the carbocat ion formed. Tertiary substrates react faster than secondary substrates, which in turn react much faster than primary substrates, because more substituted carbocat ions are better stabilized through inductive effects. Because E1 reactions proceed through the formation of a carbocat ion intermediate, they do not require a strong base. Once the carbocat ion is formed, even a weak base can remove a proton from an adjacent beta carbon, leading to the formation of an alkene. The formation of the carbocat ion facilitates the removal of the beta proton, as its bond electrons can be used to form the pi bond in the resulting alkene. Additionally, because the reaction passes through a carbocat ion intermediate, the orientation of the hydrogen relative to the leaving group does not affect the outcome. It's important to recognize that because E1 and SN1 reactions occur under the same reaction conditions, there is inevitably competition between these two reaction mechanisms. Before moving on to discussing the E2 reaction mechanism, let's discuss carbocat ion chemistry in a bit more detail. Carbocat ions act as Lewis acids, making them excellent electrophiles. This allows them to readily undergo addition reactions with nucleophiles or elimination reactions with bases. Carbocat ions are electron-deficient species, making them sp2 hybridized with a planar geometry. They have an empty p orbital that is perpendicular to the plane formed by the bonding orbitals of the carbocat ion. We've observed the stereochemical implications of the planar carbocation intermediate in SN1 reactions. Because the carbocation is planar, the nucleophile can attack from either face, leading to a mixture of products with both retention and inversion of configuration. When discussing carbocation stability, we noted that more substituted carbocation ions are more stable, similar to radicals, as they benefit from the inductive effects of adjacent carbon atoms, which help disperse the positive charge. Unsurprisingly, the positive charge on carbocat ions is even better stabilized when it can be delocalized over resonance-stabilized pi systems. The planar geometry of the carbocat ion, with its perpendicular empty p orbital, allows it to align with adjacent p orbitals in a pi system, enabling resonance stabilization. For example, in an allylic carbocat ion, the positive charge is spread over multiple positions, distributing the charge and increasing stability. Similarly, just like for radicals, the presence of more extensive pi systems that can delocalize the positive charge leads to greater stability. This is why benzylic carbocat ions, where the charge can delocalize across the aromatic ring, are even more stable than allylic carbocat ions. The final important concept in carbocat ion chemistry that we will discuss is carbocat ion rearrangements. Reactions involving a carbocat ion intermediate may be accompanied by rearrangements where a pair of electrons from an adjacent bond migrate toward the positively charged carbon, resulting in the formation of a new, more stable carbocat ion. Substrates with carbocat ions will often rapidly undergo these rearrangements to make the more stable carbocat ion intermediate before proceeding to the next step in the reaction, ultimately leading to the final product. Because SN1 and E1 reactions proceed through a carbocat ion intermediate, they are susceptible to these rapid and unpreventable rearrangements. Consider the following examples. The following secondary alkyl bromide starting material undergoes nucleophilic substitution via an SN1 mechanism to form the tertiary alcohol rather than a secondary alcohol. Similarly, this secondary alkyl bromide starting material undergoes E1 elimination to form the tetrasubstituted alkene rather than a disubstituted alkene. Both examples have something in common: the carbocation intermediate that was expected to form rapidly rearranged into the more stable carbocation intermediate, which then continued through the rest of the reaction pathway. So what caused this change? Let's explore the two common types of carbocation rearrangements, beginning with the 1,2 hydride shift. In our example of the substitution rearrangement, we observed the migration of a CH bond from a tertiary carbon to a neighboring secondary carbocation. This shift transferred the positive charge to the more stable tertiary position. This process is known as a 1,2 hydride shift, where the hydrogen, along with its bonding electrons, moves to the original carbocat ion site, forming a new CH bond. As a result, the positive charge relocates to the position where the original CH bond was. The second common type of carbocation ion rearrangement is the 1,2 methyl shift. In our example of the elimination rearrangement, we observe the migration of a CCH3 bond from a quaternary carbon to a neighboring secondary carbocation ion. This shift transferred the positive charge to the more stable tertiary position. This process is known as a 1,2 methyl shift, where the methyl group, along with its bonding electrons, moves to the original carbocation ion site, forming a new CCH3 bond. As a result, the positive charge relocates to the position where the original CCH3 bond was. Overall, both SN1 and E1 reactions can undergo carbocation ion rearrangements, including both 1,2 hydride and 1,2 methyl shifts. Since both mechanisms involve the formation of a carbocation ion intermediate, if a rearrangement can lead to a more stable carbocation ion, the shift will occur rapidly and is generally unavoidable. Now let's return to our discussion of elimination reactions and discuss the E2 mechanism. In an E2 reaction, a strong base, such as an alkoxide or hydroxide, deprotonates a hydrogen from the beta carbon, which triggers the simultaneous departure of the leaving group. This process occurs in a single concerted step where bond breaking and bond formation happen simultaneously. Below is the arrow pushing diagram illustrating the mechanism. The name E2 stands for elimination bimolecular, referring to the rate determining step of the reaction. This means that the reaction rate depends on the concentrations of both the base and the substrate, making it a second-order reaction overall. Importantly, for E2 reactions, the hydrogen being deprotonated on the beta carbon must be positioned anti to the leaving group on the alpha carbon. This alignment allows for the proper orbital overlap needed to form the double bond in a single concerted step. While E1 reactions are typically in competition with SN1 reactions, selecting for E2 elimination over SN2 substitution can be achieved by using a bulky, sterically hindered base. E2 reactions are often carried out with bases like tert butoxide in butanol, which preferentially promotes the formation of the E2 product by favoring deprotonation over nucleophilic substitution. Let's wrap up the video with a summary of the key differences between E1 and E2 reactions. The rate law for E1 reactions is unimolecular, depending solely on the concentration of the substrate. The rate determining step is the departure of the leaving group, leading to the formation of a carbocation ion intermediate. In contrast, E2 reactions have a bimolecular rate law, relying on the concentrations of both the substrate and the base. E2 reactions proceed through a concerted mechanism, where the base removes a proton from the beta carbon while the leaving group departs simultaneously. It's also important to remember that while the orientation of the beta hydrogen relative to the leaving group is irrelevant for E1 reactions, the beta hydrogen must be anti to the leaving group on the alpha carbon for E2 reactions to occur. The stability of the carbocation ion plays a crucial role in E1 reactions. More substituted substrates form more stable carbocation ions, making them more likely to undergo E1. Tertiary substrates are highly favored, while primary substrates are much less favorable due to the instability of primary carbocation ions. For E2 reactions, the key factor is the strength of the base and steric hindrance. Strong, bulky bases can effectively deprotonate the beta carbon, favoring elimination. Tertiary substrates are often preferred for E2 because they stabilize the forming double bond and avoid steric hindrance that would make SN2 less favorable. E1 reactions do not require a strong base. They can proceed with weak or neutral bases, as the formation of a stable carbocation ion drives the reaction. Conversely, E2 reactions require a strong base to drive the elimination process by efficiently removing a proton from the beta carbon. Bulky bases such as tert butoxide are particularly effective for E2 as they favor elimination over substitution. The solvent also influences each mechanism. E1 reactions are typically favored in polar protic solvents such as water or alcohols, which stabilize the leaving group in the transition state via hydrogen bonding, lowering the energy barrier for carbocation ion formation. On the other hand, E2 reactions are more efficient in dipolar aprotic solvents like DMSO or acetone, where the base remains reactive and is not heavily solvated, enhancing its ability to deprotonate. However, in practice, E2 reactions are often run using strong, bulky bases like potassium tert butoxide and butanol, which helps favor elimination over competing substitution reactions. As always, let's do some practice. Supply the missing starting material, reagents, and reaction conditions or products for each of the following reactions. If a sequence of reagents is required, specify the sequence as 1, 2, etc. Feel free to pause the video and try these problems on your own first. In the first reaction, the tertiary bromide reacts with sodium methoxide in methanol, and we need to predict the product. Due to the significant steric hindrance at the alpha carbon of the substrate and the polar protic nature of the solvent, the reaction is unlikely to proceed via an SN2 mechanism, even with a strong nucleophile. Instead, the reaction is expected to follow an SN1 mechanism. In this mechanism, the bromide leaves stepwise, forming a stable tertiary carbocat ion. This carbocat ion can be attacked by methoxide from either face, leading to a mixture of products with both inversion and retention of configuration. Additionally, the positive charge on the carbocat ion can be resolved through an E1 elimination mechanism, where methoxide deprotonates a proton from an adjacent beta carbon, forming the more substituted Zevs alkene as the elimination product. In the second reaction, an unknown starting material reacts with potassium tert-butoxide in butanol to produce a cycloalkene. Given the strong, bulky nature of tert-butoxide, this reaction likely proceeds via an E2 elimination mechanism. In E2 mechanisms, elimination occurs through an anti-transition state, meaning that the leaving group must be anti to the beta hydrogen that is deprotonated by the base. With this in mind, we can deduce that the starting material was likely a cycloalkyl compound with a leaving group positioned anti to a hydrogen on the adjacent carbon. Based on the product formed, we propose the following structure, or its enantiomer, as the starting material. In the final reaction, the given starting material reacts with sulfuric acid under heat, and we need to predict the product. To do this, we can outline the reaction mechanism. Initially, the hydroxyl group of the alcohol is protonated by the acid, forming an oxonium ion. This oxonium ion becomes a good leaving group and departs from the alpha carbon, generating a secondary carbocat ion. This carbocat ion then undergoes a rapid rearrangement via a methyl shift from the adjacent carbon-carbon bond within the cyclopentane ring, leading to a ring expansion and forming a more stable tertiary carbocat ion. Finally, this tertiary carbocat ion undergoes E1 elimination by water acting as a base, resulting in the formation of the most substituted Zevs alkene as the final product. As always, thank you for watching, and I'll see you next time.